Alright, let's kick things off with a surprising question. What in the world acts like a one-way street for electricity? No, not traffic signals. I'm talking about the semiconductor diode. Imagine it's like a tiny bouncer at a nightclub, letting current in only one direction while refusing entry the other way. At the heart of it, a semiconductor diode is a PN junction device. It allows current to flow only in one direction. When forward biased, it has low resistance, but when reverse biased, it behaves like a grumpy old gatekeeper, offering very high resistance. Think of it as an electrical valve. It controls the direction of current like your heart valves control blood flow. Now, the behavior of this smart little device is defined by a beautiful formula. I is equal to I naught times the quantity E raised to the power of QV divided by KT minus 1. Here, I is the current, I naught is the reverse saturation current, Q is the charge of an electron, V is the applied voltage, K is Boltzmann's constant, and T is the absolute temperature in Kelvin. This exponential relationship between voltage and current is the cornerstone of the diode's rectifying behavior. It lets current pass easily in one direction and blocks it the other way. No wonder we call it the traffic controller of circuits. So how does this magical one-way gate even form? Let's dive in. Picture this, you take a p-type semiconductor, chock full of holes, and an n-type semiconductor, overloaded with electrons, and gently press them together. What happens next? It's like a dance party. Electrons from the N side and holes from the P side start diffusing into each other's territory. But they don't just keep dancing forever. As they recombine, they leave behind charged ions near the junction, forming what's called the depletion region, a charge-neutral space with fixed ions and no free carriers. This region sets up its own electric field that says, "Whoa! No more partying across the junction." It creates a potential barrier, V sub B, which stands in the way of further diffusion. That's your built-in electric field, and unless we apply an external bias, majority carriers are not allowed to cross. We can even put math to it. V sub B is equal to KT divided by Q multiplied by the natural log of open bracket Na times Nd divided by Ni squared close bracket. That's the thermal voltage times the log of the ratio of doping concentrations to intrinsic carrier concentration squared. This voltage barrier is crucial. It's what gives the diode its selective behavior. Let's now look at how the diode behaves when we actually apply voltage. Imagine a roller coaster that only works properly when you push the car forward, not backwards. That's like a diode's VI characteristics. In forward bias, we apply a voltage that reduces the built-in barrier. The result? The depletion layer narrows, carrier recombination occurs like a reunion party, and boom, a large current starts to flow once a threshold voltage is crossed. In reverse bias, we hit the brakes. The external voltage increases the barrier, widening the depletion zone. Majority carriers are blocked, and only a tiny trickle of current flows, known as the reverse saturation current, symbolized as I naught. Here's our cornerstone equation again. I equals I naught times open bracket E raised to the power QV divided by KT minus 1 close bracket. This holds true for both forward and reverse biases. And on AVI curve, it's clearly visible. There's a slow buildup of current until you hit threshold, then a rapid exponential rise. On the flip side, under reverse bias, the current remains flat and tiny until the device breaks down. This curve is a signature, a fingerprint of the diode's rectifying personality. Okay, so what really changes when we bias a diode differently? Think of the depletion region like a security gate. In forward bias, we move the gate back and say, "Come on in." The external voltage reduces the potential barrier, narrows the depletion region, and invites the majority carriers, electrons and holes, to reunite and flow freely. That's why we get significant current. But in reverse bias, we slam the gate shut and add some extra bolts. The potential barrier increases, the depletion region widens, and majority carriers are now strictly forbidden. Only a tiny minority of carriers sneak through, resulting in a small reverse saturation current approximately equal to I0. But beware, keep increasing that reverse voltage and eventually the diode reaches its breakdown voltage. And then what? The gate breaks, opening the floodgates for a large reverse current. That's breakdown, and depending on the diode type, it may or may not survive the experience. So how do we put this teeny tiny one-way traffic controller to work in real life? Let's talk applications. The star role of a semiconductor diode is in converting alternating current, or AC, into direct current, DC. This is done using diodes in rectifier circuits. In a half-wave rectifier, one diode allows only one half of the AC cycle to pass through. In full-wave rectifiers, more diodes are used to pass both halves constructively. In digital circuits, diodes are gatekeepers, allowing current only in specific directions to implement logic operations like ANDs and ORs. This unidirectional magic and the exponential IV behavior form the backbone of electronic control. Remember our favorite diode equation? I equals I0 times the exponential of QV by KT minus 1. This formula is your best buddy when analyzing how rectifiers and other diode-based circuits perform. Whether it's power supplies, logic circuits, or even voltage regulators, this little device has a big job. Now let's zoom into the half-wave rectifier, a classic application. Imagine plugging your charger into the wall and your phone only gets power during every alternate half second. That's basically what a half-wave rectifier does. You feed it an AC signal, then pass it through a single diode in series with a resistor. During the positive half cycle, the diode is forward biased and conducts, sending current through the resistor. But during the negative half, the diode is reverse biased and blocks current. The result? A unidirectional, pulsating DC output. The average or DC value of this output is Vm divided by pi, where Vm is the peak input voltage. But there's a catch. Half the time, the input isn't being used, so efficiency isn't great. There are power losses during the blocked half cycles. Still, it's simple, cheap, and perfect where efficiency isn't top priority. Ready for an upgrade? Let's now meet the full-wave rectifier. It's like the clever sibling who uses both halves of the AC input. This circuit can be designed in two main ways, the center tap version with 2 diodes or the bridge configuration with 4. In both setups, different diodes conduct on alternate half cycles, ensuring current always flows through the load in the same direction. That's twice the output for your effort. For the bridge rectifier, the average DC output voltage is 2 times Vm divided by pi, definitely better than the half-wave version. And fun fact, the output ripple frequency is not equal to the inputs. It's actually double. The frequency of the ripples in the DC output is 2 times the frequency of the AC input. More output per cycle, less wasted energy, and better performance. Now that's smart engineering. Let's flex our math muscles a bit with a solved example. Suppose we are given these values. I0 equals 5 times 10 to the power negative 12 amperes, V equals 0.7 volts, and temperature is 300 Kelvin. We are asked to calculate I, the diode current. We'll use our trusty textbook friend, I equals I0 times the quantity E raised to the power QV divided by KT minus 1. Plug in the numbers. That's 5 times 10 to the minus 12 amperes multiplied by open bracket e to the power of 1.6 times 10 to the negative 19 coulombs times 0.7 volts divided by 1.38 times 10 to the negative 23 joules per Kelvin times 300 Kelvin, close bracket, minus 1. That exponent turns out to be about 27.07. So e raised to 27.07 is a massive number. Multiply it through and we get I approximately equal to 0.27 amperes. That's a strong forward biased current, perfectly consistent with what we expect. Alright, time for a quick recap. The current flowing through a diode can be calculated using I equals I naught times e to the power qv divided by kt minus 1. The built-in junction potential barrier is given by V sub B equals Kt divided by Q times the natural log of Na times Nd over Ni squared. For rectifier circuits, the average output DC voltages are V sub DC for half wave equals Vm over pi and V sub DC for full wave equals to Vm over pi. Diodes let current flow easily when forward biased but block the path in reverse unless pushed beyond breakdown. The forward current increases exponentially with voltage while reverse current stays negligible. And in real circuits, these tiny heroes are used for everything from rectification and logic gates to voltage regulation and more. They're the foundation of modern electronics. That's it for today's session. Hope you're buzzing with diode knowledge now. Remember, every time you charge your phone or listen to music over Bluetooth, semiconductors are silently doing their magic. Physics is awesome, and it gets even better when you can laugh and learn. Catch you in the next chapter.